I sure struggled while making this video, but I'm really happy with the result, and I prepared some beautiful simulation models for you. And I structured this video into 3 levels, so we will start nice and easy and we will gradually approach the more complicated aspects. Every child knows that temperature tells you how warm something is. But then again, what does warm even mean? It's a bit like telling someone that velocity measures how fast something is. It's just replacing one word with another. Of course, we have a sense for how warm something is when we touch it, but how something feels is very subjective and does not really make for a good definition. And furthermore, there are factors other than temperature that influence our thermal sensation. For example, if we place these two objects next to each other, over time we expect them to equilibrate to the same temperature. That's an important aspect of temperature that will also be important later. Still, after hours of sitting next to each other on my desk, this piece of metal feels quite cold and this piece of wood feels quite warm. How is that possible? It's because these two materials have a very different thermal conductivity, which additionally to the temperature also has a large influence on our thermal sensation. All in all, seeing temperature as how warm something feels is usually enough for our daily life, but it doesn't really bring us closer to understanding what temperature actually is from a physical perspective. To get a better understanding, wouldn't it be great if we could see with our own eyes what happens in the material on the atomistic level when we change the temperature? Experimentally, that's not so easy, but there are computer simulations that mimic the behavior of atoms, and these are amazing to get an intuition about such atomistic processes. Here you can see a simulation of a bunch of argon atoms. I chose argon because, as one of the noble gases, it does not tend to form any chemical bonds, which is great to keep things simple. Currently, the system has a temperature of 85 Kelvin. That's pretty cold, minus 188 Celsius. So cold that argon, which is a gas at room temperature, is mostly liquid. We can see that in this liquid state, the atoms move around, change their positions, but still mainly stay in this little droplet. Let's see what happens if we cool the system down further. As you can see, there's less and less movement. At some point, the atoms are still shaking a little, but they are no longer moving freely across the entire droplet. The argon is now frozen, it's in a solid state. If we decrease the temperature even further, there's even less movement, which also means that there's less energy in the system, less kinetic energy of the atoms. If we instead increase the temperature, the movement is increased, and with that also the kinetic energy in the system is increased. If we go all the way up to room temperature, we can see how the droplet quickly evaporates and the argon comes into the gas phase, the state that we expect for a noble gas at room temperature. What we can learn from observing the atoms at different temperatures is that temperature appears to be correlated to the velocity of atoms, and with that to the energy of the system. And this can already provide some great intuition about what the effects of temperature are. For example, if you imagine you touch something very hot, then the violently shaking atoms of that hot material are banging against the atoms in your finger, which in turn makes the atoms in your finger start to shake vigorously. At some point, the atoms in your finger are bouncing around so violently that structures in your skin, like proteins and that kind of stuff, get ripped apart and destroyed. And that's how high temperatures can hurt your finger. But while understanding that temperature is correlated to the velocity of atoms is very useful, it is still only something that is correlated to temperature. It's not really what temperature is. The velocity of atoms is a velocity, it's not a temperature. To really understand what temperature is, we have to dive into the statistical roots of temperature. The best way to explore the statistical roots of temperature is with another simulation model, one that is even simpler than the simulation of argon atoms. But before we dive into the model, let's recap what we know so far. Apparently, temperature seems to have something to do with the energy. At least in the case of kinetic energy, I think that was pretty obvious in the previous simulation. And in the very beginning, we briefly touched on the idea that two objects have the same temperature if they are in some sort of equilibrium with each other. That means we're looking for a quantity that has something to do with energy and that reaches the same value in all parts of the system when we approach equilibrium. Okay, now to the model where we can find out what this quantity is, find out what temperature is. Imagine a few atoms arranged on grid positions. I like to think of them as tiny marbles. And let's assume that these marble atoms cannot move all over the place like their natural counterparts. Instead, all they can do is bounce up and down. Bouncing, or movement in general, is a form of energy. So, to make our atoms bounce, we have to add energy to the system. Let's assume that for each unit of energy that we add to the system, we can put one atom into its bouncy state. For simplicity, let's also assume that there is only one level of bouncing. Atoms can either bounce or not. The law of energy conservation tells us that the total amount of energy must stay constant. So once we have set up our system, the number of energy units must not change. But nothing contradicts energy transfer between our marble atoms. Let's assume that energy units are, from time to time, randomly transferred to neighboring atoms, in which case one atom stops and another starts to bounce. Okay, so that's pretty much all we need to explore the mysteries of temperature. For example, if we add a bunch of energy units to one side of the grid and let the system evolve for a while, we can see how the energy becomes distributed among the entire grid. That's exactly how we expect heat to behave, right? Essentially, by adding energy to one end, we have made one side warmer than the other. And just like we expect, over time, the heat becomes distributed more equally. Temperature is kind of right in front of us now, but we still haven't figured it out completely just yet. To understand what temperature is, we have to understand why the system evolves like we just saw, and also when it stops to evolve. In our model system, energy is transferred randomly. In principle, any outcome is possible. But if we repeated the simulation over and over, we would always get similar results of energy essentially distributing more equally. The thing with such randomly evolving simulations is that most of the time they evolve towards the most likely state. And the most likely state is the one that has the most possibilities for how it can be realized. Let me show you what I mean by cutting the system into two parts, and let's again add a bunch of energy units to one side. For the left part of the grid, there are a lot of possibilities the system can be in. Roughly 5.5 billion combinations of different marble atoms being in their bouncy state. Such a number of possibilities is typically denoted with an omega. For the right part of the grid, there is only one possibility. Every marble atom is in its non-bouncy state. There are no possible variations. Now, if we take out one unit of energy from the left part, the number of possible arrangements in this part is reduced. If we compare the previous number of possibilities, omega E plus 1, where the E plus 1 indicates that it had one additional unit of energy compared to the current state, if we compare this with the current number of possibilities, omega E, we find that in the number of possibilities we have lost a factor of 1.47. But now, if we add this unit of energy to the right part of the grid and compare the previous number of possibilities omega e minus 1 to the current number of possibilities omega e in this part, we find that the number of possibilities has increased by a factor of 30. Before, all atoms were in their ground state, and now with this one unit of energy, only one, but any one of the 30 atoms can be in the bouncy state. That's why there are 30 possibilities now. Overall, by transferring one unit of energy, we lost a factor of 1.47 in the left part, but we increased the number of possibilities by a factor of 30 in the right part. The overall number of possibilities is the product of the number of possibilities of both parts. And this number was increased when we transferred the unit of energy to the right, which means that by transferring this unit of energy, overall we came to a more likely state. A randomly evolving system would have therefore also been likely to evolve in this direction. Now let's check what happens if we transfer another unit of energy, and let's keep track of these factors by which the number of possibilities change in graphs. To treat both grid parts equally, I chose to plot the ratio between omega e plus 1 and omega e in both cases. So that's the change in the number of possibilities if we added a unit of energy to the left or right part of the grid. For completeness, I now also show omega e plus 1 and e minus 1 as numbers for both grid parts. So for the left part, it is this factor that we're keeping track of in the graph. And for the right part, it is this factor here. Okay, now if we take out another unit of energy from the left part, the number of possibilities is again reduced. This time we lost a factor of 1.64. But if we add this unit of energy to the right part, the number of possibilities is again increased, this time by a factor of 14.5. So overall, we again increased the number of possibilities. We gained more on the right compared to what we lost on the left. But surely this can't go on forever. At some point, energy has to stop moving predominantly to the right. Let's bring the grid parts into contact so that energy can move freely, randomly between both grids, and let's see what happens. As you can see, energy continues to flow predominantly to the right until these two factors are roughly the same, until adding a unit of energy changes the number of possibilities by the same factor in both parts, until the temperatures are the same in both parts. Temperature tells us how much the number of possibilities changes if we add or remove energy, and by that it tells us in which direction energy tends to flow. Energy is most likely to go where it can increase the number of possibilities most effectively. That's simply the likeliest thing to happen, and energy stops to predominantly flow in one direction if it changes the number of possibilities by the same factor no matter where it goes. And that's what it means for two objects to have the same temperature. Now, this has probably been a lot to take in already, and I guess it would be good to pause the video for a minute to let that all sink in. But there's one last thing that we need to address. I think this factor in the number of possibilities that we have worked with so far is the best quantity to look at if you want to fundamentally understand how temperature works. Unfortunately, it's not directly the temperature metric that the scientific community has settled on. It's not the metric that would lead to the equally spaced lines on a thermometer that we are all used to. You have to see that historically, temperature was not devised in a bottom-up approach, starting from an atom and then figuring out how a few of them interact. Instead, people looked at large systems, volumes of gases or liquids, and observed their behavior. And unfortunately, the reasonable choice for a temperature metric in this macroscopic approach is not necessarily the most straightforward choice from a microscopic perspective. Which means that there are, let's say, a few mathematical complications between this factor in the number of possibilities that we have stumbled on in our microscopic model and the temperature metric that we are all used to. We have to do some formula reshuffling to figure out how the two are related. This is the definition of temperature, or rather the inverse temperature, 1/T, that you can find in a lot of textbooks. That's the one that leads to the equally spaced lines on your thermometer. 1/T is defined as the derivative of the entropy S with respect to the energy E. Now, entropy is an interesting topic on its own, and you can learn more about it in one of my other videos. All we need to know here is that it's a metric for the number of possibilities. More precisely, entropy is the logarithm of the number of possibilities. We will make use of that in a minute. Now let's say this curve represents the entropy S as a function of the energy. Then this derivative is the slope of the tangent line for any given point, which tells us how much the entropy is changing with respect to the energy of the system. In our microscopic model, however, we have been looking at a discrete system. We worked with discrete units of energy. A derivative doesn't really make sense for a discrete system, but we can calculate the equivalent slope by dividing delta S from one step to the next by delta E. Delta S is the difference between the entropy of one point and the next. And if delta E is just one unit of energy, we can further simplify the equation. And now we can use this formula from before. Entropy is the logarithm of the number of possibilities omega. We can plug that in. And finally, we can use logarithm rules to come to this form. And as you can see, temperature is indeed not directly this factor omega E plus 1 divided by omega E, rather a logarithmic variant of this factor. But don't worry about this too much. I think going through the formulas was important to give you the full picture, but for our intuition, this doesn't really change a lot. Temperature still quantifies how much the number of possibilities changes if we add or remove energy. Introducing this logarithm makes it a slightly different metric, but one that is still fundamentally measuring the same thing, a change in the number of possibilities. Also note this 1/, relation, which unfortunately means that we have to flip everything in our head. A high temperature actually means that there's a small change in the number of possibilities, and vice versa. Here in the beginning of the simulation, for example, in the high temperature part of the grid, the number of possibilities is changed by a small factor if we add or remove energy. In the low temperature part, on the other hand, the number of possibilities is changed by a large factor. So that's what this 1/, part in the formula does. Anyway, at the end of this video, I would like to close the loop from this very abstract model where it was easy to count the number of possibilities back to this model closer to reality, the simulation of argon atoms. Of course, it is hard to count the number of possibilities here, all the different combinations of positions the atoms could have, all the different velocities the atoms could have. But we can still apply the same logic. In the current situation, due to the attractive forces between the atoms and the lack of energy, the atoms are confined to stay close to each other. If we added energy, we could overcome some of the bonds between the atoms, which would allow them to explore more of the accessible space. Therefore, adding energy would drastically increase the number of possibilities the system could be in, which means that it's a low temperature. Here, on the other hand, there is enough energy so that the atoms can fly all over the place anyway. If we added more energy, the number of possibilities wouldn't change that much anymore. A small change in the number of possibilities means that this is a high temperature. If we brought two such systems into contact, energy would be likely to flow from the hot system on the left to the cold system on the right, because that is where the energy can increase the number of possibilities more effectively. The energy transfer to the cold system leads to more possibilities overall, and more possibilities means that it's more likely, and likely things simply tend to happen. And that is how temperature gives the flow of energy a direction.